So this is the second WIAA technical workshop of this year, the first of the spring semester, and WIAA tries to host these technical development workshops that are sort of geared towards applying concepts that we learn in class, sort of applying them to real world applications. Because it's one thing to sit in class and learn about these theoretical concepts, and it's easy to say, how is this applicable? But we try to sort of take it one step further and show you the application in a physical sense. So I'll be talking about, well, my name is Nick, first of all. I am the graduate technical chair with WIAA, and we'll be talking about computer-aided design and some important design tips that I think are important to share with you. This thing in the bottom left corner that's called a cyclocopter. It's a hovering MAV, micro aerial vehicle, and that's a CAD model in CATIA. CATIA is a little more daunting than other CAD programs. And to the right, that's a sort of broken out version of a quad rotor biplane, which is a VTOL type unmanned aircraft. That rendering is done in SolidWorks. Everything was done in SolidWorks. Just quick about me, I'm a second year master's student under Dr. Chopra in the Rotorcraft Center. So my focus is on hovering things, and particularly electric vertical takeoff and landing, hence all of these cool projects. I like to focus on VTOL configurations and flight control and stabilization, but if you're testing code or you're testing theory or something, you need hardware. So in order to build hardware, you need CAD. What we're going to be going over, what is CAD? Why do we have it? How does it fit into the design process, which I'll talk a little bit more about. And then we'll just cover some very basic intro concepts of CAD for, just for the sake of completion for anybody that's unfamiliar. And then we'll move over to some demos in SolidWorks. Now, if you don't have SolidWorks, I'll show you how to get access to it. But if it's not your preferred CAD software, that's okay. The basics that we'll cover are basically universal across CAD software. Just the placement of some buttons and the naming of some things are a little different, but Google is very much your friend when it comes to learning these things. So what is CAD? Well, I pulled the definition from Wikipedia: the use of computers to aid in creation, modification, analysis, or optimization of a design. That's very helpful. Computers designing something, it's in the name. But we can think about CAD as the ability to create individual parts within the computer, and these parts are represented by solid bodies or meshes that we are able to create through different operations, either extruding a part into the third dimension and then adding additional extrusions, or like lofting between two different planes, and then also as a part of CAD, we're able to take these parts and we're able to see how they fit together. And this is really useful in, checking to see if the parts are the right size, just looking at some of the mechanics of how they move and interact together. And these two things are unrelated. That part is not a part of that assembly. It's just a picture that I stole from Google. But, CAD also takes it a step further and allows you to do some analysis on your designs. So we're not just talking about, designing a part. CAD sort of encompasses all of this. And this is, when used effectively, CAD is sort of a process where you're able to design a part, put it in your assembly, analyze it, and then iterate back to design changes at the part later. I just thought this picture was really cool. I've seen this meme. It's not really a meme, but it's shared around in engineering forums. And before computers, before CAD, it was just warehouses of engineers that were drafting up blueprints. And I think that was really cool how collaborative and creative they had to be. But nowadays, any dude with a laptop can just sort of open up SolidWorks and design something like we're about to do. And for some reason, he has a really large croissant there. I thought that was funny. But we've really come a long way, and CAD is a really powerful tool. Perfect segue. CAD is a very powerful tool in the design process. So I wanted to sort of structure this presentation less on, here's CAD, here's how you extrude something, here's how you do this. But I really want you to think about where it fits into the design process and how you can use it and leverage it to, you know, create a product. And because, you know, oftentimes the goal is not just staying in conceptual design. We want to break out and actually create a product that is usable and useful to people. So, you know, once you have an idea, you can immediately hop into CAD design and come up with a concept, and then you can start analyzing it. And you know, oftentimes you bounce back and forth between design and analysis, and this sort of informs design decisions in the computer. But you know, the computer's not always right, so sometimes we have to break out into the real world and prototype. And this is a very important process of the design process. Um, you know, it's like I said, computers are not always correct, and it's really good to validate design choices on a, you know, physical hardware. And of course, this is all iterative, so there's a lot of back and forth here that you're basically doing just to optimize your design and flush out bad ideas and make sure everything fits together and works in a cohesive project. And the end goal is to spit out, you know, a refined CAD design that you can manufacture. And you know, when we're talking about you know, the concept of critical design review, I know a lot of students had just finished up some of that. You know, you want to have sort of a vehicle that you can present and say, here, we're ready. Here's a vehicle that we can manufacture. You know, we've validated everything. Here you go. So that was just sort of a high level overview, but I do want to make sure you have the resources, you know, to use CAD. And if you're a University of Maryland student, you're very lucky. We have a lot of options in Terpware. An open, I don't know if it's open source, but a free to use software called Autodesk Fusion 360 is very common and popular among, you know, hobbyists and people that are not in academia. It's kind of limited in its scope, but it's really good, you know, mesh generator for solid bodies. The next step up would be like Autodesk Inventor or AutoCAD, and this is used a little bit more in the industry. And you can get that on Terpware. And I will provide these links. I will share the slides right after this presentation in the chat, so you'll have them. Another option, CATIA. CATIA is sort of, you know, it's a little different. It's a little more daunting. Their architecture and their framework is a little bit, it deviates a little bit from other CAD software. So I wouldn't recommend it as a starting point, but it's definitely a good skill because it is used in the industry. And you can get a free student trial from their website. SolidWorks is my personal favorite. You can get it on Terpware, but another thing that I've also used is their student sponsorship program. I thought you all should know about this. If you're on a student team or like a research project, you can basically email them through the student sponsorship program and tell them you're on a team. Tell them how many people are on your team, and they'll basically send you bulk licenses for SolidWorks for a year. And it's really handy, and I've used it many times, and I'll probably use it many times in the future. Siemens NX you can get on Terpware. This is sort of like I like to think of it as sort of the big brother of SolidWorks. There's a little more analysis tools available, and it's I believe this is what they use over at SpaceX. So it's very much common in the industry, and we have access to it. Talking a little bit more about the design process and where CAD fits in, I just wanted to walk through, you know, the process of using CAD to develop something. So first, obviously, you need a problem, and you're trying to develop a solution for it. The first thing you should immediately start asking yourself and asking your team is, you know, what manufacturing methods and resources are available to you? You know, if you don't have a 3D printer, then you can't start designing 3D printer parts unless you're willing to, you know, invest the money and buy a 3D printer. You know, if you need a part machined out of steel or aluminum, you better make sure that you either have a CNC router, you have somebody that knows how to use it, or you're able to outsource that work. So, you know, oftentimes I see people designing parts that are impossible to manufacture, and you have to make sure it's reasonable. And that goes all the way back to the very beginning of when you start in CADing. You know, this has to be in your mind when you're making your design. Next up, you might want to start thinking about, you know, any solutions that are already available that can make your life a little easier. You know, obviously you don't want to start machining your own nuts and bolts. Those already exist. But, you know, something a little more custom, can you adapt it for your problem? Or if you can't, either way, it's time to start hopping into CAD. And this is just sort of a mush of iterative design. There's no real arrows in here. It's just sort of, you design in CAD, you might analyze in CAD a little bit. You might break out of the computer and start prototyping and testing. If you are working with a 3D printed part, it's really easy to throw a part on the printer overnight. Next morning, check it, see if the parts fit together, then immediately make your changes in CAD again. But ultimately, the one thing that stops this iterative process from going on forever until you have a perfect product is a deadline. And 9 times out of 10, the deadline will be what forces you out of this. And you might not have the perfect final solution, but you better have something that you can present as manufacturable when you're trying to design something like physical. So what I'm really trying to hammer in here is, it's one thing to design a part, but another to design a part that can be manufactured. It should always be in the back of your mind. So just stepping through this assembly here on this vehicle that I've worked on, I just thought it was a good example of sort of a complex assembly in CAD. But every single part on here, we had to think about manufacturing methods from the start. These spars and ribs are all laser cut plywood. We have a laser cutter in our lab, and if we didn't have a laser cutter, then we would probably have to source out maybe a box beam or something, but then we couldn't get some of these custom profiles like the airfoil and all of that. So the laser cutter really helped us. We needed a custom rotor spinner to enclose some of the mechanics of the rotor. And the simplest solution for that turned out to be 3D printing. And this is a case where 3D printing was the optimal solution. But on a project this big, printing some of these other parts like the ribs and the spars is just not feasible. There's not 3D printers big enough, or that we have access to at least. The rotor blade grips are CNC machined. We do have a CNC machine at our lab in the Rotorcraft Center. So we are able to machine these, but we really had to be careful about designing a part that, we're able to actually tool and machine, because really complex geometry becomes very difficult to machine with only a 3-axis CNC. And finally, well, not finally, but this next one, we spec'd out a carbon tube. And, you can manufacture this yourself, but it's really difficult. But, people do sell pre-manufactured tubes and stock. So we were able to source this existing product, this existing carbon tube from Rockwest Composites. So just a short story, I was on a design team and we needed a wing spar for a wing. And somebody spec'd out a rectangular carbon spar for our box beam, and turns out nobody sold the carbon spars in those dimensions because it just didn't exist, and there was no way that we had enough time to actually do the carbon fiber layup to manufacture that box beam ourselves. So we ended up having to adjust our design and find something that was already existing. And the last thing, this entire skin of this aircraft is actually carbon fiber reinforced polymer layup. And designing this part itself is not that difficult, but you also need to think about, the required framework to actually manufacture this. So this required, 90% of the work was not in designing this one part in CAD. It was more so directed towards designing the plug and the mold for the carbon or for the composite layup that would allow us to manufacture this. So there's, for this one part, this one wing part, there's probably 20 other parts that were required to make the plug and the mold to manufacture this. And of course, don't design things that in CAD that are, we aren't designing ourselves. Like if we're sourcing out a servo, we can just, steal some solid bodies off the internet. We don't have to waste our time on that. A motor or sensors, oftentimes if you can just do a rectangle to sort of as a sort of mass simulator in your CAD model. Only worry about the parts that you're actually manufacturing. Any parts that you're sourcing, see if you can get alternative models. Speaking of sourcing CAD models, GrabCAD is a great resource and I highly recommend it. You know, you can get electronics, sensors, actuators. Here you can see there's just a motor. This is an obscure drone motor, and there's, you know, multiple CAD models I can download and put into my project. I would advise you against, you know, if you have like a mechanism that you're trying to model, like a scissor lift or something, you know, don't go to GrabCAD and find a scissor lift model and then try to finagle it into your application. You know, that's your design work. But if there's like a consumer product that you're purchasing, definitely, you know, try and make your life a little easier and find these models online. McMaster Carr is a supplier of mainly hardware, fasteners, and all of that. But what's really nice about them is, you know, if you're buying your hardware from McMaster, they also supply 3D models of pretty much all of their inventory. So, you know, if you're speccing out a bolt or a gear from McMaster, you can download the solid body direct from their website and import it into your project. And you can see if it works before you even order it. It's awesome. So before we get into CAD, I'm just going to talk about some basic things for completion, and then we'll talk about the rest in SolidWorks. You know, we know what a part is. A part is just a single solid body in an assembly, and you can actually break your assemblies up into sub-assemblies. And depending on the scope of your project, you might want to take your master assembly and break it up into sub-assemblies, and then within the sub-assemblies, they can have other sub-assemblies. So in this case, the rotor sub-assembly, I guess sub-assembly, appears 4 times on these other sub-assemblies. So if we just make one, then we can import the sub-assembly into this project, and then everything else comes into one of these sub-assemblies, and then everything else comes together in the master assembly. So if you're smart about sort of setting up your workspace before you even start CADing, you can, you know, do really complex projects later on down the road. So parts, just a formal definition, they're comprised of 2D sketches that have been extruded to form 3D bodies. You can do a standard extrusion, a revolved extrusion, which is sort of revolving around some axis that you define. This is good for, you know, rotary parts or cylindrical parts. And a loft is also pretty common, where you have multiple sketches and you sort of interpolate between the two to fill in a solid body. And you can use any combination of these in a part. You know, CADing is sort of like sculpting, except instead of starting with a block of, you know, a square block of marble, you're starting with nothing and you're building up the marble. It's really interesting. You can also, you know, take things away. So if I wanted to extrude away a cavity in the side of this, that's also an option. And assemblies are comprised of multiple parts, obviously, and they fit together with a series of constraints. And this is important because when you're constraining your assembly, you need to make sure that you know, you're applying enough constraints so that it is fully defined. So one constraint is needed for each degree of freedom in the body. And if we talk about degrees of freedom, there are 3 translational degrees of freedom, X, Y, Z, translating, and then you can rotate about those axes as well. So, you know, a body in CAD has 6 degrees of freedom that you need to properly constrain. Some types of constraints we'll talk about in SolidWorks. Some types of constraints, they'll constrain 2 degrees of freedom at once, just due to the nature of the constraint, or even more. But, you know, ultimately we need to constrain every axis that we want. If we don't, then the parts can move, and sometimes we want them to move. In the case of, you know, demonstrating the mechanics of this rotor system, the pitching axis of the rotors is a free degree of freedom, and therefore the mechanics allow it to move within CAD. So now we're going to go into the demo in SolidWorks. I just want to preface what we're doing as our demonstration. So we're going to design a small little motor mount to attach a small drone motor to a square pylon. And the square pylon can be thought of as like the arm on a drone or something like that. We're going to do this 2 ways. One way with a 3D printer, and that'll just be a single solid part, just to show you, you know, the advantages of 3D printers sometimes. But if you don't have a 3D printer, you also have other options. So we'll talk about, you know, considering a laser cut plywood type design. And ultimately, like I said, we're just going to try and design a part that will mount this motor to that pylon. So I've sketched up, some napkin sketches of my idea. That's always the first step, sort of, just sketch up your idea so you have sort of a path moving forward. On the left is the plywood sketch that I threw together in a minute. I know the size of the plywood pylon. It's a 12 millimeter square. And I'd like, the length that it interfaces with to be 20 millimeters. With the plywood one, we'll do a tab slot construction that gives more surface area for, gluing plywood together. And then we'll just, we'll assume that we can just glue the plywood to the motor pylon. For the 3D printing case, it's a very similar design, except that it's 3D printed. It's a single part. We don't have to worry about that. So I'm going to stop the share here and then pull up SolidWorks. If you guys have any questions, feel free to either, interrupt me, no worries, or throw them in chat. But I'm going to pull up my SolidWorks here, and I'll share my screen again. And let me pull up the chat just in case anybody. Okay, so yeah, this is the motor. I grabbed this from GrabCAD. This is just a standard drone motor. One thing to do is in SolidWorks. So let me sort of familiarize you with what we're looking at. I'm navigating the part, in SolidWorks with the center mouse to rotate, and then I can zoom in and out. That's sort of how I translate around as well. But over here, this is the part that I downloaded from GrabCAD. We'll talk more about this, but this is sort of like the part timeline or the workspace. And this is where all of the operations required to create this part were done. You can sort of see the different things that are being highlighted. Up here is all the tools. In SolidWorks, there's features. Features pertain to, a solid body. Sketch pertains to when we're dealing with a sketch on a surface, on a 2D surface. These are, drawing lines, drawing circles, drawing curves, dimensioning. And the rest of this is sort of, external to what we're focusing on today, but there's also some simulation things. Evaluate, we can measure things on the evaluate tab. This is very useful. So if we're designing this motor, we have to know how to mount it. So I really quickly just measured the distance between the centers of the mounting points, and it's 16 millimeters. So we'll remember that for when we start building. So, and then this is just our spar. If we measure it, we see it's 12 millimeters, and that's what we're fitting our part to. So I'm going to start a new part. And the first thing we need to do, so now we can see we're on a blank part. There's a front plane, top plane, and a right plane. And there's nothing else down here. So we have to start building. So I'm going to select the top plane and then go to the sketch tab in SolidWorks. And again, this is almost universal across CAD software. It's just a matter of, where are the buttons? But the terminology is fairly identical. So when I select sketch and I have the top plane selected, it starts a sketch on the top plane. So the first thing I'm going to do is using the circle tool here. I'm going to draw a circle, and we're going to use this circle to draw the motor mounting holes. So those were 16 millimeter away from each other, and there were 4 of them. And what I'm going to do really quick is I'm using this circle to denote that 16 millimeter diameter circle that those mounting holes lie on. And I used this dimension tool to basically put in the dimension of 16 millimeters. Now, one thing I know is that this circle is going to be this isn't actually a line that we want to deal with later as far as extruding it into a 3D body, but this is more so called construction geometry. So we're using it to sort of reference other things. So I can select it in SolidWorks and tell it to be construction geometry. And that basically just means we're, it's not a real line. It's just, we want to reference it sometimes. So I'll draw another circle here and I'll dimension it. So I know those holes just because I know that motor are M3 holes, which means they're 3 millimeters. But because, you know, the threads are slightly larger than 3 millimeters, it needs a little more. So, and I don't want to be tapping into this. So we'll go a little higher. We'll go about 3.5 millimeters on this. This can be tuned. So now we want 4 holes. So I'm going to go up here in the sketch tab and select a circular sketch pattern. And this allows us to sort of take this part and mirror it around the circle. So if I select it, it's pretty, SolidWorks is pretty smart. It automatically detects that this is the center. And there's already 4 of them, but if we had 5 holes, we could change it to 5 of equal spacing, but SolidWorks is pretty smart. And there we go. I'm just going to quick add another circle in the center because I know the motor has a little extended shaft that we don't want to be poking the material with. And then we can add our external circle. And you know, the dimensions of this are kind of obscure, but I'm going to match the diameter of the motor. And I know the diameter of the motor is about 28 millimeters. And so now we can see if I were to go extrude this to say like 3 millimeters, you know, we can see we have sort of a solid body that we've just created, and we can mount the motor to this, but you know, it needs a little more in order to interface. So I just, I'll undo that. Go back here. Okay, so what I'm going to do is I'm going to do another sketch line straight down. And this is going to be construction geometry. And then I'm going to draw a line and draw a line. And this is sort of going to be where the that 12 millimeter pylon will interface. When the entities, the sketch entities or the sketch lines are blue in SolidWorks, that means that they're unconstrained or they're undimensioned. So when we add a dimension, I'm just going to do that for now. We'll properly dimension in a second. When they're fully defined, they'll turn black, which means, you know, we can't click and drag this because it's fully defined. So I know that our pylon is 12 millimeters, but I want to have 1.5 millimeter wall thickness around it for the mounting point. So we'll do 7.5. Whoops, sorry, wrong one. 7.5 on here, and this is only the half width of it. And then we'll mirror this. I selected the things we want to mirror, and we're going to mirror about this construction line. And there we go. So now let's go out and then we'll go to the features, and then we can extrude this into a solid body like we did just before. And I'll select this, and I want it to be 3 millimeters. This is sort of, you know, obscure dimensions for now, but I wanted this to be 3 millimeters. And we have this part. Now we sort of have to, this is sort of a baseline part, but now we can start, you know, adding more sketches and adding more, you know, adding more features to this base part. So you can actually add a sketch to a face that we just created. And I'm gonna basically extend this section up because this section needs to be thicker so that we can fit that 12 millimeter square tube into it. So I've selected the face, I started a sketch on it, and a cool tool in SolidWorks is this Convert Entities tool. Basically, I can select a face and it'll just draw a sketch around it. It's pretty useful. And, this area up here is what I really care about in terms of making it thicker. So I'm going to extrude that. Change the direction. Actually, no. So we're extruding from, so this will be, oops. Yeah, so we select it. I want this to be, so we extruded 3 millimeters. And I want this to end up being a square, but we have 1.5 millimeter wall thickness on top of the 12 millimeter. So it'll be 12 millimeters extruded from here, and that gives us a square here. And I'll just check my math. 15 millimeters, 15 millimeters. Okay. So now, we want to stick the pylon in here. There's multiple ways to do that. We could either do a sketch on here, on this face, and we could draw a rectangle, and we could dimension this to be, our 1.5 millimeter wall thicknesses. Whoops. Didn't like that. Anyway, I'm not going to do that. I'm just going to show you another tool, just for the sake of expanding our skill set. But you can use what's called a, let me exit the sketch. We don't actually want to use the sketch. What's called a shell command. And a shell command, when I select this face and I tell it how thick I want the shell to be, in my case, 1.5 millimeters, it creates a shell with this face open on this solid body, right? So now we've effectively made the cavity that we can slot that 12 millimeter wooden pylon into. And this should be, if I did it correctly, 12 millimeters, perfect. Now in the real world, you're gonna be doing, what's called tolerancing for parts that fit together, because, you're never gonna have perfect 12 millimeter square tube. It's probably going to be a little bigger, so you want to account for that in your design. With this method, as we make these changes in the timeline over here, we can go back and we can change some numbers later on to account for that tolerancing. But for now, we're going to work with exact numbers just because it makes it easier. This part could work interfacing that motor up here to the pylon down here, but one thing I don't like is, having this sharp corner. And if we're going to 3D print this, we might as well make the geometry a little more complicated if we can improve the strength. So I'm going to go to the Features tab in SolidWorks, and I'm going to pull up the chamfer command. Chamfer basically just takes a corner and it makes a 45-degree angle like that. And you can actually, you can change some of the parameters here so it's not just a 45-degree angle. So in this case, I'm going to select this type of chamfer, which we provide it with 2 parameters, D1 and D2, the distance from the edge here and the distance from the edge here. And I want to pull this chamfer to be from this edge to this edge. So D1, I think, is going to be, whoops, nope. I think D2 is going to be 28. No, not 28. I think it was 27 was the diameter. Close enough. Doesn't matter. And then this one will be 12 millimeters, and that pulls us all the way to the top. So if I hit confirm on that, we've effectively made our part much stronger. We don't have that hard corner. We don't have the hard overhang. And this will be a much sturdier part. It won't break up here. One last thing, we just created an issue was, now if we're trying to put screws through this to mount to the motor, we don't have a flat angle that we're screwing them into. So we sort of have to carve away some material here that'll allow us to screw the bolts in for the motor. So another thing I wanted to show you, which is very convenient, is what's called a reference plane. So if we select this face we know that we want we know that we want a carboy material so that it's parallel to this face, and we go in and we insert some reference geometry, a plane, and it basically creates a new plane offset from this one. And I'm going to change the offset direction, change to 3 millimeters, and that puts us right in there. So that's where I want, the head of my screws to lay on this part, on this plane. And we can just go start a sketch. And I'm just going to really quick make another circle here on the sketch of that plane. I know that the head of the M3 screws are 6 millimeters. And then I'm going to revolve them like this. So we have 4 of them. And then we can go and we can cut away that material. And it cuts all the way through. If we want, we can extend it. So now we can get our bolts in there down to a good size, and this is a very strong part. The last thing I like to do, this part would work fine, but if you have the ability, go in and fillet any hard corners. It really makes a difference in strength. These corners I think are the only ones I really care about on this part. And there, now we have a motor mount. So I just wanted to sort of highlight the purpose of this timeline over here. This blue line we can drag in SolidWorks, and it'll sort of revert the part to a previous state. All of these other operations that we performed to get to that final solid body are grayed out. And this is pretty useful because you can sort of see how the part is built one operation at a time. And what's also nice is we can go in and we can say, the tolerancing that I talked about earlier for the 12 millimeter spar, the spar is actually 13 millimeters or about 13 millimeters. So we can go and we can edit the shell command later, and we can say, we want our shell thickness to be 1.25, and that'll give us, if we it's 12.5, it should have been 1, but do your math correct and you can get a 13 millimeter hole here now. So it's just a matter of, you can change your things from earlier on, and I'm going to undo that. So now that was, this is a 3D printed part. It's a single part. It's great. It'll work. But let's design something really quick using those same principles for a laser cut part. And it's sort of a different approach in that there's going to be multiple parts. So let me just save this really quick as, call it a 3D printed part. And then let me just, so we don't lose all of our progress, let me just save this as a laser cut part. So now we're working on a laser cut part. I'm actually going to go in, I'm going to select everything except for that first extrude. I'm just going to delete all of it. Sorry, I'm just reverting the part. Okay, so we're going to start from here. Same process as before, but now we know that, we're laser cutting some plywood, some 3 millimeter plywood for this assembly. We can't do those complex geometries where we extend some parts of it up and some parts of it down. And I mentioned I want to do that slot and tab system, so I can go in here, I can edit the sketch, and I can, cut a little slot in here. And I know that this needs to be 3 millimeters for the 3 millimeter plywood. Let's just arbitrarily say that it's going to be 8 millimeters, and let's put it 8 millimeters from this end, or how about 5 instead of 8? 5. Okay, so that's it's all blacked out. It's fully defined. I'm going to mirror this just by selecting the mirror entities tab in the sketch tab and mirror about that. Puts it there. And we exit the sketch this time, and now those tabs are cut out. So another thing that I briefly forgot is that, let's check this dimension here. So that's 9 millimeters. So we actually need to increase the size of this so that the internal diameter will be 12 millimeters. So it'll actually be 9 millimeters will give us 12 millimeters for that 12 millimeter spar. Okay, so we'll go back, we'll exit the sketch, it makes those updates. Great, so this is our part 1. Now we need to create some side pieces, and then we need to create a bottom piece. So if I save this, I'll start a new part, and I will start a sketch on the top plane, doesn't quite matter. And what we can do, you know, we have the power of dimensioning. We can sort of just sketch out how we want this part to look like. And then we can dimension it later. And I'm just drawing a center line with construction geometry. Remember, construction geometry is not, you know, it's not seen as a line, it's just used as a reference. Now, I know that I want this, I want this tab to fit into that slot in the other part. So it has to be 3 millimeters tall. And we knew that the length of the tab was 8 millimeters. And then we knew that the distance from the one end was 5 millimeters. And the distance from the other end, I don't actually know right now. We'll go back and check the other part. And then we know that this needs to be 12 millimeters for our case. And we can make changes later if we mess up. But now everything's black, everything's fully defined. Let me go back to the other part really quick. So we want this part to go 7 millimeters this way, just for our sake. We can tweak it later. So that would change this dimension. And we can go and extrude this 3 millimeters. And fatal mistake, I forgot to mirror the tab. This is symmetric, so let me do that really quick. That's why I put it in the center line. Now we can extrude it. And this is 3 millimeter plywood. Great. And I will save this. My directory, and now as we're building the parts, we're just going to start constraining them in our assembly. So this is we'll start a new assembly, and I will insert the begin the assembly by inserting the first laser cut part. And the first part you insert by default is sort of the anchor part. It's basically fixed in space, and everything else is with reference to this one. And then I'll go and I'll insert the second part. And now we need to get this part constrained to this part. So we'll go to the mate. Mate is just another word for constraint. And you can see in the mate tab, there's multiple different mates that you can select. Coincident means you select 2 points, and they'll 2 points or 2 lines, and they'll touch each other. Parallel means if I do a parallel constraint on these 2 faces, just to show you, it forces this face to be parallel to this face. Now that is just that just constrains 2 degrees of rotation. It's still free to translate in space pretty much anywhere it wants, but I didn't want that, so let me undo that. What we do want is a mate of this face to this face. Hold on, sorry. I don't think I didn't delete the original mate, and it didn't like it. So let's go back and try that again. This face to this face, right? So now that is good. And now we know that we want our tab, the top of our tab here, to be at the top of this face. And that's the wrong direction, but that's okay. We can change the mate alignment here. So basically there's 2 solutions there, and SolidWorks didn't know which one was correct. So we've added 2 constraints that constrain rotation as well as translation with the coincident mate. So now I know for a fact that this piece only has 1 degree of freedom anymore. And that degree of freedom is here. We wanted this part to slide around, great, but we don't. We want this to be here. And now, if we try and click it, it tells us the selected component is fully defined. It can't be moved. That means we fully constrained our system. So if I click Control and drag the part, it just creates a copy. That's a little shortcut in SolidWorks. It's pretty handy in big assemblies. I'm going to really quick mate this second one up, just following the same deal. And SolidWorks is pretty smart. It'll auto select the right mate, but if we don't want that mate, we can select a different type. And all of them are just coincident. We want them to be touching. And now this part is fully defined. Right, so the last part we need is just a bottom part to close this up, and then we're done. So let's go ahead and start up a new part. And I'll start a sketch on any plane we want. Just before we start actually sketching, let's get some numbers here. Ideally, you could write this down, but so we know that we need our part to be 18 millimeters, and we want it to be 20 millimeters. So 18 by 20 with these 2 tabs cut out, and this tab is 8 millimeters long, 5 millimeters from one edge. That's all I needed to know. So in our sketch, really quick, I'll just start hashing this out to make this quick. So I need to be 18 by 20. And we needed to have those little tabs cut out. Tab is for 3 millimeter plywood. We said it was 8 millimeters. And it is it was 5 millimeters from one side. I need to make a center line that we can mirror about. Go and extrude it, millimeters, and we save it. And we can go over to our assembly that I haven't saved yet, but that's okay. Always save your projects as often as possible. We'll insert that final part. And we'll start mating it. It doesn't really matter what you made it to, as long as you have those 3 primary constraints that will lock it in place. So I know this face right here has to go to this face, and I know this face has to go to this one, and then that guy goes to that guy. I think we're done. So 2 different design approaches for the same part, depending on what options you had available to you. Let me actually, I'll just insert the 3D printed one right here alongside it in the same assembly. So, 2 different parts, 2 different manufacturing styles, but regardless of what resources you have available to you, you're able to still, still produce something. And this is a great start. This would be a great start for a prototype. One thing I would probably change eventually is, maybe instead of relying on gluing the wood in, I would add some bolt holes so this can be removable. Maybe I might add a piece right here that would lock this, prevent the spar from sliding in and out. But for first iteration, for demonstration's sake, this is fine. Let me just insert the motor just to verify. And so just typical mates. I know this surface goes to this surface. Now what we can do What's useful for like rotating things is the concentric mate. If I select a circle and another circle, SolidWorks will automatically select a concentric mate. And this is good. This is cool when you have things that are supposed to rotate, because it's locked, but it'll rotate. So, I prefer not to do that for this motor, for example, because we have mounting holes. We might as well mate those mounting holes. So here's the mounting hole on the motor, and then here's the mounting hole on this, and we need at least 2 of those to lock it in place. And there we go. So, this part would work fine, and I hope that was pretty helpful in, exploring different manufacturing methods and getting familiar with, some of the CAD processes. So yeah, that's all I got, and hopefully that was useful.